All right, welcome back to episode number 52 of the Piezo SHOCK Show. Today I'm going to demonstrate on our famous dental transducer um, that we have here. And we're going to talk about if putting this transducer tip in water can actually improve our can it actually improve our performance or our ability to characterize and understand the device. So let's go ahead and characterize the quality factor. I'm going to have to hold it because I'm going to hold it in a pool of water that I'm going to pour into. So I'm going to characterize it while I'm holding it and also after we put it in water to see what happens. But firstly, when we're just firing up this transducer, I'm going to make sure that well, it's tightened properly, more or less. I can't really get a grip on it because it's not its original case, but we're going to talk about this soon. And we're going to keep analyzing this. We're going to analyze it with its own driver soon. And so let me just go ahead and show you how water is poured into a bowl, into a cup. Now, you have to do this slowly because if you pour it too fast, you might spill. So spilling usually makes a mess, and messes are usually not good. So I recommend that you pour slowly and you don't make a mess. Now, this is what we're going to be doing. We're going to be dipping it in the water, and I'm going to be running it. But right now, we'll just have it sitting by itself on this table there. And let's go ahead and analyze the transducer as we had before. Okie dokie. So let's run it from 1,000 to 40,000 kilohertz or 40 kilohertz and increments of 100. And we'll run the sweep, and I do want it to be an impedance and phase. That's what I like to see here. And we want to probably change it to logarithmic just so we can get an idea about resonance and anti-resonance both. And as we knew from the last video, we're going to have some activity here. These two resonances that occur, and I believe these are the ones that are going to be operational. So we could actually extend this range, and I'll probably put this at, let's put this at 200, and let's extend it to 50,000 if you're just curious about that. Notice the phase is close to -90 while it's in the capacitive region. We have a couple of resonant points here. We're going to be analyzing this area. I believe this is the working frequency. That would be obviously best confirmed from what the driving frequency is and doing other measurements, but let's take a look. So let's run a sweep from 35, let's do from 33 kilohertz to, even let's just do 45 too. And that just gives us this. Let's do 44 because 45 is not, well, 44. Yeah, and then let's just put it down to 10. But let's do that. And let's just wait for this data to be taken. This is again the transducer sitting in air, just like that. And I'll open up our friend Excel. So resonant frequency 1, resonant frequency 2, resonant frequency 3. We're not going to be able to tell the quality factors right now. And this is and then we're going to do water. And I'll put all these in probably in kilohertz. And I'm just demonstrating some of the characterization techniques that you might be looking for in your transducer there. So we have these cursors that I can use. So the resonant frequency is already determined there. These cursors, cursor 1, and I'll put cursor 2 there. All right. So we have a resonant frequency at, okay, it redoes everything after it's done. Not a problem here. So we'll stick him there. It's cursor number 2, we'll stick it there. So the first frequency, okay, it's been a little bit tricky. Okay, so the first frequency is 35.72, which is that. 35.72. The next one is at 36 here, 36.82. And the last one is at 42.4. 42.4. Now I'm basically interested in seeing how damping of the tip in water is going to affect the performance. It can also give us an idea about what's best coupled to the output, because whatever mode is going to be damp more, well, that's the one that's going to be pushing water around most effectively, and hence that's going to be also the mode which is going to be active. So we also have the quality factor around this resonant point here, because this is what the program determined as a minimum impedance. So we have a resonant frequency of a Q of 306. So I'm just going to write Q factor, and we'll just keep a note that's going to be for the second resonant mode. We'll keep that in our brain for now. And we'll also keep its impedance here at 937 ohms. Also, I'll call this Q2 because it was a second resonance, and Z2, 937 ohms, which is actually pretty high for a transducer. If you want to put a lot of power into it. Now I'm going to hold it, and hopefully, and I'll just show you here in the corner. I'll stick that to the side and stick this. So I'm gonna hold it like this. And then I'm going to well, actually, I'll just hold it from the back here. That should be good enough for me. Then I'll run that sweep again. I'm trying not to hold it hard, although it's kind of inevitable that I will damp the transducer out when I hold it. And it doesn't look very good, actually. It did zap the impedance a bit, but not an extreme amount, I would say. But let's get this reference data, and after that, well, we will be able to analyze it. What do you say? Okay. Let's just align these cursors back up where we had them before. Okay. Okay, there you go. So 35.69. Oops, that's actually, yeah, that's still resonant. These it's still on all in order. So 35.69 was our first 5.69. This is not water, this is held in air. I'm holding it. And then we have 36.76. Which is just a little bit lower. It's probably due to damping. And the last frequency is 37.18. Oh, hold, sorry. It's a 42.36. So a little bit of damping there. The reduction in frequency. And the quality factor is 167. Ooh. That got a smack there. And 1.57 kilohertz. Sorry, 15700. Sorry, 1570. So 1.5. This is ohms. So there you go. And quality factor obviously has no. It has no units. Let's just make colors. It does help to view. Okay. The next is held water, the tip in water. What does that look like when we view it? It's going to look like this. We got our cup of water. We put slowly, and I'm going to dip the transducer in water like so. I'm going to hold it, hold my breath, and take a measurement. And this program can save all of the data, obviously, but I'm just doing everything quickly and for demonstration purposes. So this could actually be a very consistent test platform to like dip your transducer in water to a certain extent. You can have fixtures, you can have jigs. Now, depending on how I'm holding it, the impedance is going to be shifting around a little bit. I'm not using a very consistent method for holding it. And as you see here, I put the transducer back down. Now that we're done, oh, the Q increased. Not really, but let's take a look. It's not a really good test setup, I would say, to say the least. But let's take a look. So the first resonant frequency was 34.79. So that definitely increased 34.79. So I think we see some mass loading there. The resonant frequency is 36.64. So that didn't change very much. This frequency was most affected by just the water. And here we have this frequency being 41.16. So 41.16. Interesting. And the Q factor is 215. Which seems like I was holding it a different way. That's okay though, 1.06. I'm not promising perfection by any standard with this measurement, but we'll continue. This is the data taken. What I want to show here next is, well, now, what if I just hold a tip? Now, this is not very like, I would say scientific. If I just take here and I just hold it, or even, I guess I could put it like on the edge, like have it like this, because I know this tip is like wiggles. So I could lightly press it on the edge. Oh, good way to do this. Yeah, how about I use this wrench? Might catch it at a node point, which wouldn't matter, make a difference anyway. Okay, how about just like that? All right, I'll just hold it up in the air like this, with back my finger, holding it and suspending it on the wood. So it's kind of just under, I'm kind of just balancing it under its own weight. That could be a good, so I'll call this tip balance. And let's see what that looks like here. Probably in practice, when you actually have it at the right frequency and amplitude, you'll be able to tell which mode sprays water around the most. That's the one where you're going to be wanting to work, more than likely. But right now, our amplitudes are quite low. We're using low voltage, like 2 volts, pretty much driving. So we're not going to spray water anywhere. But we'll get to that pretty quickly here soon. This is actually what I wanted to show. I saw this earlier. When the tip is loaded, there's those two frequencies kind of merge together, which is nice because now you have a single operating point. Those frequencies won't really get too confused with each other. Now the power delivery may change, and that may have to do with the design of the transducer. This resonant frequency mode seemed to have really took a hit and went downward or got damped out completely. It may not work here. But here we have a resonant frequency which actually increases at 808. And I'm just gonna concentrate here, 36.710. And the Q factors, I guess it's 262. It's hard to tell though, because we are really two resonant frequencies close to each other. It doesn't end up working. So 262, it seems kind of high for it to be completely loaded. It may actually be this resonance. I can say I really don't know. 808. So we're exploring, and we're going to find out in about a second, like in the next few episodes, what this transducer is actually driven at. Is this the actual mode? But let's just say the tip hold. So this was on wood. I have a screw here. And I'll do something else here now. And I'll just hold a tip and we'll try it like that and see what comes out. Using the actual device, we'll have damping from the higher power, and we'll also have damping from when there's impact. So we're just going to take a look at how well this mode is coupled to damping at the tip. Now, when this is actually impacting teeth, there could be a bit more impact. See, this is pretty good here. If So for a real resonant device, if you just hold the tip with your fingers, you shouldn't be able to destroy, like completely eliminate the resonance. So I would say that 42 kilohertz is not the real operation point. Just holding the tip should not be able to completely eliminate it, even though it is heavy damping. Like right now, we're at Q of 50, and the resonant frequency is 36.650. When I held the tip. So let's go here, 36.650, and the Q is 50, and the impedance is 3.35. So I would look for, in the final device, I would look for a situation where you can measure something like this. Not holding the tip is going to be kind of problematic. I'll give another recommendation. I'm going to pour the water back, and I will show, and because holding it with your finger is not really a systematic way of doing it. This is actually a little bit rubbery, so it's kind of like a finger. So let's say you could load your transducer in a fixture or holder, and you can press against it, press the tip against the rubber surface with enough amplitude. Let's say press the back of the tip, like press it like this. Let's say I haven't worked for a company, designing these type of transducers, but I'm just giving like a general kind of like, well, you could do this, you could do that. Like this is different. These might be different ways of evaluating that resonant frequency, because obviously it behaves much more differently. There's a singular resonance when it's damped, when I had that finger. So that's useful for measurement. So let's just try that. So again, we're trying it against this soft holder here. Hopefully it doesn't slip away from us while I'm using it. Okay. So I'm just gonna go ahead and start that. I'm going to hold the back part of the transducer a little bit tighter in order to get that. We still got two modes there pretty clearly. I didn't like how when I pressed this transducer tip against the wood, it completely damped out that 42 kilohertz one. I'm actually curious whether that could be the operating mode, or it just lives in this area, because there is a larger impedance. So that actually simulated that mode as well. So at this point, I'm going to resign. I'm really not sure just from measuring transducer like this, what frequency is going to be the operational one. Now, I did a little bit of testing already on the driver, and there did seem to be frequencies in this range, as well as occasionally something at 42 kilohertz. It was a little bit mysterious, but there you have it. There could be some different ways of loading your device, and this there are many, and in that loading process, you're able to eliminate spurious mode. That's kind of what I wanted to show, although this demonstration was a little bit imperfect. I wanted to show that the loading process can eliminate spurious modes that you find when the transducer is completely unloaded. Or, you know what, I want to try something. I want to try loading the transducer like it is in practice. And that'll be last go I have for today. So if you remember, we had this O-ring, there is this holder that goes here. and there's his back piece, right? There's his back piece that goes there. Let's just show you that like that. So I'm going to hold this, I'm going to clamp it in between my fingers and there, and perhaps that will give us actually what we're looking for. I would not be absolutely not surprised. So let me run it like that. So this is practically clamped in the holder. I'm not squeezing it too tight, but I am holding it tightly. And I'm wondering if this is going to be a double frequency. It seems like it might be. Yeah, it continues to be that double frequency, which the Q factor kind of increased here. Unique. Becomes sharper, but I think still high impedance. Or maybe the spurious modes shift around when you do load that. And you know, if this mode right here gets knocked out, then it's got, I'm not counting on it at all. But actually, yeah, the jury's out for that. But this coupling seems so small that I'm really doubting this is the operating mode. This is actually being a little bit of a mystery. So there's two resonant modes here, and sometimes we operate devices in between two modes in order to simulate more than one type of you want elliptical or some other type of motion. They're purposefully done. I might have to research on this specific device. I feel like it's not targeting that, but I could be wrong. Water didn't damp the device enough to be able to merge the modes like I would have hoped, but some devices can be heavily loaded and repeatedly loaded. So you can use it for a characterization. So kind of talking in summary, let's stop the screen share. Yeah, so talking in summary, so we had this transducer. I tried, I showed you the differences between frequencies and holding it and putting it in water and pushing against wood and holding the tip. What I really wanted to try to show was that the spurious modes merge together when you loaded the transducer, so you'd be able to more repeatedly characterize it in an industrial environment, in like a manufacturing environment. But it didn't seem to work as well with the transducer. It may be something that is purposefully played into for the operation. It could be some elliptical mode where you are simulating more than one resonance, or you maybe just driving it with higher voltage and you're using off resonance. So we're going to take a look. There was this 42 kilohertz mode, which seemed to be a remnant of the longitudinal mode of this transducer itself. You saw that in earlier videos, but we're gonna dig in. So the next video, I might want to dig into the driver and actually probably hook it up to the driver and see what it's doing, get some water spraying around, also look at those frequencies so I can be a little more sure about how the device is operating. So you've been watching episode number 52 of the Piezo SHOCK Show. Please sign up for updates for whenever I release a video. You'll get presentation notes and a brief description of the video, what I'm talking about, right to your email. Please comment and share these videos with anyone who might be interested in them. Also check out my consulting offerings where I provide transducer development support for companies developing ultrasonic transducers like this one. So we're all going to be experts at the time we're done analyzing this. I haven't worked on this specific type of dental transducer before, but transducers do have similar fundamentals. So we're going to do some investigation analysis. We'll do some we're going to get down and dirty with this guy. All right. So thank you for watching, and I will see you next time.